Hello, today we want to wrap up our discussion on classical wave equation and talk about classical wave equation and different boundary conditions for finite system, boundary conditions on finite systems. This is where we get standing waves. When we are going to try to apply classical wave equation on infinite systems, we are going to get what is called regular waves or moving waves, or so we are going to study that that kind of waves, progressive waves, later on. But right now we just look at finite systems. So finite systems means there are ends. You have two ends. You have a bar or a spring or a string. There's a finite size. So that's what finite system means. So let's recall, in each of the systems there's a displacement variable. So displacement, and we had two types of displacements, but we can use the letter psi, and we're going to look at one-dimensional system. So in that you have something along x-axis and at time t. So this says displacement. Psi is different things in different systems. So in a string, psi was, if this is the y variable, and so this is x, so this is psi xt. For the tart spring of tart string. If you had a then it was here in a spring, you had at this point x, how much this was stretched, so that was psi x t. In a bar, I had a bar which may have been fixed at both ends. Then we looked at what the deformation of this thing at different times. So they have take different variable in a tube. So you have a tube filled with air. Maybe you have both ends closed, so you have x, and so this is the x. We will say at that location, what's the pressure from the ambient pressure? That will be psi of xt. So we have different things that psi may represent, and in each of these systems we have a classical wave equation that tells the dynamics of this variable. And we can write it in a d square psi dx square equals 1 over v square psi dt square, or we can write as d square psi dt square is equal to v square d square psi dx square. One of the two forms, right? Boundary condition refers to what happens at the two ends. So there are three types of boundary conditions that we deal with. One is for instance here the tart spring is, we dealt with that. That's both ends fixed. that says that this variable psi, let's call this 0 and this is L. So psi 0 t, so at any time this would be 0, and psi lt 0. So these are the boundary conditions that say what the value of the displacement variable would be at any time at the two ends. The other one is maybe one end is fixed but one end is free, and free would mean the derivative will be it will have to be tension free, so that would be derivative will be 0. So one end fixed, other end free. Say x equal to 0 and fixed, and x equal to L and free. In that case we have psi of 0t 0 and d psi x t dx, but evaluate this at x equal to L, that will be 0. And the third one is both ends free. So these three boundary conditions we usually deal with. X equal to 0, 0. So note I didn't put 0 there. First I take a derivative and then evaluate this, because this is a continuous function, and this is dx. Then we evaluate this. And d psi xt dx, and then evaluate x equal to L equal to 0. Okay, so the solutions, what the solutions will look like. So we can call it boundary condition 1, type 1, and boundary condition type 2, and boundary condition type 3. So let's look at boundary condition type 1. That solution will have to satisfy these two. It's a general solution, general normal mode solution. They look like psi of x t is going to be some kind of a cosine kx plus b sine kx times, say, cosine omega t plus phi. That's the general solution, and we will try to find solution in which phi is 0. Case phi equal to 0, this referred to starting at rest. So we would not use phi, we would just use this. And so when we ask this kind of solution, this type solution, when you have a product, this is a function of x and this is a function of t. When you have a product solution, that's actually leads to the normal modes that are allowed in these cases. Okay, so when we put it in there, we would have a different, depending on which one of these, there will be restrictions omega and k depending on which one of these. So let's see, boundary condition 1 is when x equal to 0, I want it to be 0, so then becomes a cosine omega t equal to 0. So this will be demanding psi 0 t equal to 0, that just says a cosine omega t. Note I'm using phi equals 0 equals 0. That means a equal to 0. That means satisfying this means psi of xt, this product solution, it just has sine part, sine kx cosine omega t type. Now, so this is first one, and the other one I want to satisfy psi lt equal to 0. So I don't go back to that, I just use this and try to figure out what those will be equal to. So this will be b sine kl cosine omega t equal to 0, and this is for all times, so that's not 0. If this was 0, then psi will be 0 identically, so this is not 0, so I require this to be 0. Sine kl equal to 0, and this just says k will have to be, kl has to be n pi, and n can't be 0 if n, that will be k equal to 0, and that will make it psi equal to 0. So n will have to be plus or minus 1, but if you plus or minus, I can pull the sign out, and b will be just exactly inverted of that. So yeah, I get just this has unique answers. So these are the different solutions in terms of k. So we can say k n equals to n pi over L. Now when we put this solution into equation 1, it already says that on the left side you're going to get k n square using psi denoted as xt, denoted as b sine kn x and omega nt. Kn square is equal to 1 over v square omega n square. It's going to be minus sign here and minus sign here, they will cancel, and then this is this means omega n equals to knv, just positive roots. So omega n and kn are related in normal mode solutions. So because the solution is going to be psi, we got a whole bunch of solution. We got b sine k nx cosine omega nt. So this is a solution, and where kn is equal to n pi over L, and omega n is this, and n equals to 1, 2, 3. So these are the whole bunch of solutions for boundary condition 1. Okay, you can proceed further, but let me go to boundary condition 2, for instance, or what the solution will be in boundary condition 2. So, boundary condition 2. And that's all we're going to do. And I'll let boundary condition 3 for you to practice, okay? So boundary condition 2 is psi of 0t is 0. So this just means we start with psi of xt, the product solution, a cosine kx, just plus b sine kx, cosine omega t. And start with that, and so this would mean, again, a equal to 0. That would mean psi xt simplifies to b sine kx cosine omega t. So far it looks the same because this condition is same. The second condition is I need to take a derivative of this and set to 0 d psi dx x equal to L equal to 0. So when I proceed that, I get b k cosine kl cosine omega t equals 0. Now this is not 0, and this is not 0, and this is not 0, then cosine KL is 0, cosine KL equals 0. If you go back to boundary condition 1, a condition was sine KL equal to 0, so that was the condition. But here cosine KL is 0, that means KL has to be equal to, you can see multiples, odd multiples of pi over 2. So n pi over 2, and n has to be 1, 3, 5, and so on and so forth. If you want to write for all n's, you can generate that 2m plus 1. So if you get, then you can say m equal to 0, 1, 2, 3, and so on and so forth. If you had n equals to m prime minus 1 with m prime 1, 2, 3, and so on. So you can write this in these two different ways. Let's write it like this, and instead of m, we call this m prime, call it m. So k n is 2n minus 1 pi over 2l, and n being 1, 2, 3, like this. And again, we have omega n equals to kn times v. Therefore, we're going to have a whole bunch of solution, and we have, let's see, so got some constant going, sine kn x cosine omega nt, but kn now is different now, is 2n minus 1 pi over 2l, but omega n equals to knv, and n is 1, 2, 3. So this is a different, you can say, wave numbers, and similarly different frequencies, different frequencies. Now you should try boundary condition number 3. When you do boundary condition number 3, you are going to get a very kind of similar type of thing as this. So you get you say, well, start with psi xt equals to a cosine kx plus b sine kx, and you have a cosine omega t, and then you will have a d psi dx will be minus ka sine kx plus kb cosine kx cosine omega t. But the boundary conditions will be this stuff evaluated x equal to 0 is 0, and this same thing about x equal to L equal to 0. And these two you will solve. Let me just quote from the book what the answer will be, and you should practice this. So it will be Kn will be n pi over L with n equals to 1, 2, 3, but omega n will still be v times Kn, but the psi xt will look like a cosine knx cosine omega nt. So you should show this. I'll stop here for this video.